Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to give an example of how to handle frictional forces when you have something like a belt or maybe a rope wrapped over some sort of drum type of geometry. So in this problem, we're going to try to calculate, well, let me back up and describe the problem first, I guess. Imagine that we've got this 500-pound cow hanging from some sort of rope here, which is hung over this drum-shaped geometry and tied to this 150-pound sheep. And what we're going to try to calculate here is the coefficient of friction required here between the sheep's foot and this surface to keep this system static. It's important to realize that this drum is not free to rotate. So if the rope starts moving, it's a sliding situation. All right, we're going to assume in this problem we've got a 0.8 frictional coefficient between this rope and the surface. So I've already went ahead and labeled a couple of force vectors here acting on the drum. I called the tension in this part of the system T2, the tension in this part of the system T1. It's important to realize that tension will vary along here. Also important to realize that tension 2 is going to be bigger than tension 1 because of the frictional force interaction between the rope and this drum. Now, a free body of the cow, I'm not going to do it because I want to try to keep the video short, but a free body of this cow would have tension 2 up, 500 pounds down, and that's it. Sum of all forces y direction equals 0, hoping to keep this static, shows that tension 2 would be 500 pounds. Now that tension is going to vary along this path, and in my previous video about this, I talked about how to draw a free body of this little piece here and use that free body to find a differential equation relating tension 1 to tension 2. And I'm not going to go through that in this video. I'm just going to take the results that were given towards the end of the video. The relationship now between tension 2 and tension 1 is going to be this. Tension 2 is equal to tension 1, e to the coefficient of friction times whatever this angle is between where tension 1 is applied and where tension 2 is applied. In this particular problem, that angle is pi over 4. So tension 2 is going to equal, so tension 2 we know. Tension 2 is 500 pounds. And that's going to equal tension 1, which I'm going to calculate here in a minute, times e to the 0.8 times theta. And again, this angle in this problem would be this angle, which would be pi over 4. So what I'm going to do here is I'm going to take a moment to grab a calculator, pause this, and calculate a tension 1. All right, folks, so I'm back here. I went ahead and calculated a value here for e to the 0.8 times pi over 4, and I got 1.87. Solving that for tension 1, we get 267 pounds. So now, moving on to this part of the system here, I'm going to go ahead and draw a free body of the sheep. Now already I can see, this is not very optimistic for either the sheep or the cow, but I'm going to go ahead and move on with, how do we analyze the system. Copy, paste. All right, so now free body diagram of our sheep here is going to have, and again, I'm still going to assume static, even though I see that that's extremely unlikely. We're going to have a tension 1 acting left, a gravitational force acting down, a normal force. Now there's 4 normals basically. I'm just going to lump those all together into one normal. Up. Where that normal is applied here is not going to be really relevant for the problem, so I'm just going to go ahead and leave it there. A frictional force acting left along the feet. So there's our free body of the sheep. Not worrying left or right about where that normal force is applied. It's just not going to be relevant here. I'm going to go ahead and write a pair of equations. Sum of all forces y direction equals 0. And that tells us that the normal minus the mg for the sheep. Now the 150 pounds is mg for that sheep. So our normal force is 150 pounds. Second equation, and again, I'm going to look at what I'm trying to do. I want to calculate the required coefficient of friction for this system to stay static. I realize it's, most people watching this realize it's very improbable that this is going to be static, but I'm still going to be optimistic for the sheep and the cow. Sum of all forces x direction equals 0. I'm going to go ahead and do right positive, so we're going to have the frictional force minus tension 1 equals 0. So the frictional force is going to equal tension 1, 267 pounds. Now the frictional force and the coefficient of friction I should say the frictional force is related to the normal force through the coefficient of friction. The frictional force is the coefficient of friction times the normal. This guy is 267 pounds. Our normal force is 150 pounds. So the required coefficient of friction to keep this thing static would be 267 over 150, which is 1.78. This is not probable. Not going to happen. Frictional coefficients, remember, typically are bound between 0 and 1. They don't have to be. There are a few special case scenarios, but 1.78 is a very improbable frictional coefficient between the sheep's feet and whatever the surface is. So probably the system is not going to stay static. This cow's probably going to start accelerating down, sheep left, and he's probably going for a ride, but that's okay. It's just an example. And again, the main part of this example was to demonstrate how to handle the rope over this surface here with this frictional coefficient. And again, you know, technically it's a differential equation. You draw a free body of a small piece of this, and then you calculate the difference via integration between tension 2 and tension 1. I went ahead and just used kind of the results of that integration. I mean, I don't think we have to go through the integration every time. That's in the previous video. So I hope this demonstrates how to deal with friction for belts or ropes. Have a great day.